Hello. In this presentation for DCASE 2020, I will show work we've been doing at Siemens on microphone array optimization for autonomous vehicles using the Radon transform. I will first discuss the motivation for using audio for vehicle environmental perception. I'll then talk about the challenge of designing a microphone array for autonomous vehicles. I'll spend quite a while on the technical detail of our beamforming operator, and that will lead us to the microphone array optimization method. In current autonomous vehicle implementations, multiple sensors of different modalities such as cameras, radars, and lidars are installed on the vehicle. Each sensor has a different field and range of view, and is designed for specific applications. These sensors provide a lot of environmental information, but they are limited to objects in the line of sight. When driving, human beings also use the acoustic wave field as an input. We listen to the road. This is particularly useful in situations where specific road objects are not in the line of sight. At Siemens, we have been working on classifying and localizing various road objects based on their acoustic signatures. This paper focuses on determining direction of arrival of road audio objects using microphone arrays. We performed a controlled experiment on our campus where we localized the sound coming from an emergency vehicle siren driving in a parking lot in the trajectory shown by the yellow line. We had built a microphone array consisting of 11 microphones and positioned it where the yellow square appears on the map. We applied our beamforming method based on the Radon transform to the array data. Here is the view of the scene from the array level and a visualization of the accurate sound direction of arrival we get from our beamforming as the vehicle moves from left to right. An array this large, however, is impractical for integration into an autonomous vehicle. To make audio localization feasible for vehicle manufacturers, we need to provide a solution that is both low cost and can be mounted in specific regions based on automotive design limitations. Our methodology was to split the large array into identical small subarrays, distributed at various locations on the vehicle. The separation into subarrays provides the flexibility to comply with the constraints imposed by autonomous vehicle design. For example, that the array must fit into existing sensory infrastructure. We ideally want to keep the number of microphones to a minimum to reduce costs. Additionally, because of the large bandwidth of input audio on the road, we have to consider the spatial sampling of the wavelengths that vary by an order of magnitude, and this issue is also addressed by having multiple subarrays. I will now talk about our beamforming operator, namely the tau.p transform. This transform is the cornerstone of our array geometry optimization. The tau.p transform is the same mathematically as the Radon transform, except that Radon is typically the operator name used for image processing. Here the data and axes represent something with physical meaning. Consider that we have a wave field, U, recorded by a microphone array with axes x and t. The tau.p transform is basically a summation of the data along lines with slope p, starting from time tau at zero offset. The slope p is delta t delta x, which is the inverse of velocity. We call this slowness, and it's in units of second per meter. The tau.p operation is essentially the same as the delay in some beamformer. However, having the concept of slowness in mind enables us to think about beamforming differently. While slowness is a property of the transform, apparent slowness is a property of the wave field data. Apparent slowness depends on the angle of incidence between the wave and the array axis. The tau.p operator will produce a maximum if we sum along the apparent slowness in the data, as is shown over here. If we know the medium velocity, which we do for air, then we can deduce the angle of incidence from the measured slowness. For example, consider a plane wave propagating parallel to the array axis. Applying the tau.p transform, we would measure the maximum possible slowness, which is equal to the medium slowness of 0.0029 seconds per meter, the inverse of medium velocity in air. From the data, we can deduce that the angle of incidence is 0 degrees. For a plane wave propagating perpendicular to the array, all the microphones would record the arrival at the same time, and we would measure zero slowness or infinite velocity. We would deduce that the angle of incidence was 90 degrees. For a 2D array, we can apply a 2D tau.p transform, where now we have slownesses px and py. In this case, waves arriving from any horizontal direction would have air slowness, while waves propagating vertically would have zero slowness. We transform the tau.p operator to radial coordinates, as shown here. The absolute slowness is the RMS of the slowness components, and the angular slowness is the arctangent of the ratio between the horizontal slownesses. Since we only care about sound events coming from the horizontal plane of the road, the only radial slowness we actually need to measure is air slowness. To better explain the concept of the radial tau.p transform, let me show you some field data. We recorded road data with a microphone array on top of a car. What you see here is the 2D tau.p transform of the data summed over sliding time windows. Notice that you can actually see cars propagating in front of the vehicle, going from left to right. Here's another one. Now notice that it's following the contour of air slowness. And that makes sense because these vehicles are indeed on the horizontal plane, same plane as the array. They're driving on the road. Soon you will see a siren coming from the front right and going to the back right. Here it is. The purpose of this slide was to show that energy that came from the plane of the road always goes along this air slowness contour. Yes, but any energy that did not come from the horizontal plane of the road, i.e. energy that came from the vertical directions, either above or below the vehicle, will have lower slowness. And that is effectively noise, which means that we can use the tau.p transform as a type of noise filter for energy that did not come from the surroundings of the vehicle on the plane of the road. Now that I've explained how we use the tau.p operator to apply beamforming, I will now show how we use this operator to optimize microphone array geometry and response. Recall that we only care about audio events coming from the plane of the road. These arrivals will have air slowness, and therefore we don't need to apply the transform with any other radial slowness. I remove PR from the equation, and we now have an angular tau.p transform. I define this transform as the adjoint operator f prime. The reason I call this the adjoint is that it transforms from the recorded wavefield data space U to the tau.p model space psi. The forward operator f takes the tau.p model space as an input and outputs wavefield data U. However, what I just said isn't perfectly accurate. Our data space is spatially sampled by an array. The wavefield data generated by the forward operator needs to be spatially sampled to produce the wavefield U. This is done by the spatial sampling operator S, and this operator is effectively the microphone array geometry. The objective of the microphone array optimization is to find an array geometry S that optimizes angular resolution in the tau.p space psi. Let's look at the elements we have for the optimization. We first define G0, the desired array response, in the tau.p domain. We've introduced phi s, which is the true azimuth angle to the sound source. An ideal array response would resolve the beamforming angle p phi exactly equal to the true source azimuth phi s for all incidence angles. The width of the diagonal in the response is effectively the main lobe width we would like to have. Note that we also want there to be no side lobe energy. We can specify this desired response any way we want, increasing or decreasing the magnitudes of the main lobe or the side lobes. The next element is the tau.p forward operator, which we've discussed. Then we have the sampling operator S, representing the array geometry. The operator can be seen as a matrix with 1s at microphone positions and 0s elsewhere. We have the adjoint tau.p operator that transforms from the data space back to the tau.p model space. When we cascade these operators and apply them to the desired array response, we get an estimated array response G tilde. This response is dependent on the sampling operator S. The final element is the objective or loss function. This function tells us how close our current array response is to the desired response, and we can apply weighting to emphasize specific angles of arrival. Here is the optimization workflow. Again, we start from the desired array response, apply the forward tau.p operator to get the data domain, sample the data domain with a specific array geometry, and then apply the adjoint tau.p operator to get our estimated model given the current array geometry. The objective function compares the current response and the desired response. The optimization itself is stochastic, meaning that we modify the array geometry with every iteration and calculate an objective function for every resulting array response. The internal optimization loop permutes the array geometry under certain constraints, measures the array response for each permutation, and then calculates the objective function. This process continues until a set number of iterations, or until an array response with sufficient angular resolution is found. We also implement simulated annealing in the inversion to gradually reduce the magnitude of the array geometry permutations. We started this talk by saying that our purpose was to design a microphone array that would honor vehicle design constraints. But what exactly are the design constraints for mounting sensory equipment on an autonomous vehicle? As you can see from these photos of various prototype autonomous vehicles, the technology is still emerging and there isn't a unified standard just yet. However, note that the other sensors, the cameras, lidars, and radars, are all separate, identical units with a small form factor, and they tend to be roof-mounted. If we want a microphone array that would conform to the current trend, rather than designing one large array, it's a good idea to think about multiple subarrays and maintain some flexibility. We start by considering the roof edges of a vehicle as the most likely area to mount microphone subarrays. This is the region between the small and the large blue rectangles. We constrain the microphones to only translate within this area. Each subarray can translate and rotate independently, but they must all have the same shape and size. Observe the array permutations over iterations. We make sure the arrays are identical because, from a mass production point of view, it's much better to have just one single design for any given device. We limit the maximum and minimum distance between the microphones, and we also prevent the subarrays from overlapping by limiting each one to a separate region. We calculate the array response for each individual subarray, and also the response of the whole composite array. The sum of these responses is our estimated total array response. The summation is possible since the tau.p operator is linear. In this movie, we again show the microphone array geometries as the optimization progresses. Here are the corresponding array responses for each one of the geometries shown. We actually calculate the responses for thousands of array realizations, but here we only show the ones for which the response improves. On the bottom left, we show the objective or loss function value. Since the optimization is stochastic rather than a descent method, the objective function can increase or decrease with iterations. Observe how the measured array responses become more similar to the desired response over iterations, indicating that the modifications in array geometry are indeed improving the angular resolution of the array. To summarize, what we've shown in this video is a microphone array angular resolution optimization for autonomous vehicles. The final purpose is to determine the direction of arrival of specific road audio objects that are relevant to the driving mission. The optimization itself is based on the tau.p transform. We group the microphones into identical subarrays to both reduce production costs and to conform to vehicle design considerations. Thank you for your attention. You can email me, Ohad Barak at Siemens.com, if you would like to hear more.